Last time we introduced a few new things. One of them was the abstract concept of a normed space. So that was just a vector space over F, which stands for either R or C. So it's a vector space together with a function called the norm, which is always real valued and which satisfies these axioms. Any normed space gives rise to a metric just by taking the norm of the difference, and that's how the usual metric on Rn, or at least one of the usual metrics on Rn, arises. Then we discussed, if you like, a generalization of that normed space, which was obtained by taking any compact Hausdorff space together with an integral, which is some linear functional on the space of real-valued functions on X, satisfying a positivity requirement. So that space, so that's an integral pair, that thing that I just described, and then we take F-valued continuous functions on X together with a norm, the p-norm, which is defined for p greater than or equal to 1, any real number, using the integral by this formula. We proved last time that that satisfies the axioms for a norm. And in particular, it gives rise to a metric. The metric which is obtained from the p-norm is denoted dp, and, well, just reading off that formula, that's the metric that says the distance between two functions f and g is the pth root of the integral over x of the difference to the power p. Okay, so that's a metric, that's for free, from the fact we proved it was a norm. Okay, so that means we've got this infinite family parameterized by real numbers p of metric spaces, or rather metrics, all defined on the same space. And taking p equals infinity works as well. So if you take the infinity norm, I didn't discuss this last time, it's an exercise, so just define the infinity norm to be the thing you'd expect. So it's the supremum of the absolute values. And that's bounded for the usual reason, because x is compact and f is continuous. Okay, so that exists, it's a number and it gives a norm, and the metric which is associated to that norm is just, the thing we've been using for a while. Okay, so that's the usual d-infinity metric on the space of functions. We've lifted it now to a norm, that is, it arises from a norm. Okay, so that's some explosion of new mathematical gadgets, right? All right, so there is some order to this new zoo of objects, and we're going to steadily now start imposing that order to understand what's going on. Now remember, the overriding point of why I introduced these new spaces, we already had this guy, right? We already had this metric space. Well, maybe it's interesting that it comes from a norm, okay, so maybe given the applications I've sketched of this space of functions, perhaps you're willing to believe that's worthy of existence, but okay, so you remain unconvinced that you should care one iota about some gigantic family of new metrics with no appreciable value. Fair enough. Okay, so now what we've got to do is convince ourselves these new metric spaces or normed spaces are actually good for something, and that's what we're about. So the first part of today's lecture will be convincing ourselves that those metric spaces are rubbish because they're not complete. Okay, so I said that already. So we're going to look at a counterexample that shows that that's not a complete metric space, and that motivates then taking the completion. At least that has a chance of being a reasonable object, and indeed it's a very beautiful and fundamental object, the LP space. Okay. But first I need a lemma. Okay, so we're going to talk about completions of metric spaces today. And for that, I need the following lemma, which I mentioned last time. In fact, I've used it already, so let's prove it. The lemma says, if I have two continuous functions into a Hausdorff space, which agree on a dense subset, then they must be equal everywhere. Okay, intuitively you should believe that, because think about everything, every point in X can be basically, think about the metric space version. Every point in X can be written as a limit of a Cauchy sequence in A. Applying F and G to Cauchy sequences commutes with taking the limit, so F must equal G on anything. Okay, so that's an argument in metric spaces, but we can prove it in general. So consider the continuous map, which is X goes to X cross X. That's the diagonal. You've been looking at that for the assignment. And goes to Y cross Y by taking F cross G. Those are both continuous maps, so this is X goes to the pair X comma X. So that's continuous. And Y is Hausdorff, so the diagonal here is a closed subset. Right, so maybe let's write it delta Y. So that's Y comma Y and Y cross Y for Y and Y. Okay, so that's closed because Y is Hausdorff. Okay, but that means the pre-image under this thing, let's call it, I don't know, T. The pre-image under T is closed. We can compute the pre-image under T, right? The pre-image under T of delta Y is all those x's in X such that T of X is in delta Y. Well, what does that mean? That's all the x's in X such that, well, T of X is F of X, G of X. Right, that's what that says. And that needs to be in delta Y. But a pair is in delta Y if and only if the two coordinates are equal. So that is X in X such that F of X equals G of X. Okay, so we know that's closed. But we also know that A is contained in it. Right? Because by hypothesis, every point in A has the property that F of it is equal to G of it. And, well, so that's closed, and that's dense, so we must have that that is everything. But that's what we asked. Okay, so F equals G. Okay, so, yeah.
Why that's closed and that's dense?
Why does this follow?
Yeah.
Yeah. So to say that A is dense, one way of saying that is that the closure of A is X, but that's precisely logically the same thing to say that if Z in X is closed and Z contains A, then Z is X. Okay, so let me explain this equivalence here. So what's this definition? So A closure means the intersection of all closed sets containing A. Equivalently, it's the smallest closed set containing A, because intersections of closed sets are closed. Okay, so to say this is equal to X is to say that any closed set containing A is equal to X just by the way that's defined. So that's what that says. Yeah. Okay, so all right, so what we're going to do, so in our example, A is going to be some metric space that we care about, like that one. Well, we don't care yet, that's what I said, but okay. You believe you're going to care, maybe. So that's some metric space. X will be its completion, and then that tells us that if you have a continuous map out of the completion, well, like if I start with a continuous map from the metric space, there's at most one lift of that to a continuous map out of the completion. So that's what that does for us. Okay. All right, so Okay, so we know that for p equals infinity, that is for x compact Hausdorff with this metric on CTS XR or XC, it doesn't matter, that metric space is complete. I claim that as soon as I take p less than infinity, the resulting metric space is not necessarily complete. I mean, it's complete, for instance, if x is a finite set of points, right? Because then that's just r to the n, which is complete. But let's take, for instance, x equals 0, 1, and p less than infinity, and I'll show you a Cauchy sequence in this that doesn't converge. And actually, I mean, it's not just some random counterexample. This exhibits a very important feature of these spaces, namely the particular Cauchy sequence I show you, its limit is something which is interesting. Okay, so here's the picture. So there's 0, there's 1, there's a half, okay, so take n greater than or equal to 4, and I can look at the function so fn is going to be a function on 0, 1, and it's the following picture. So it's 0 until 1/2 minus 1 on n, and then it makes a straight line up until this point, which is a half plus 1 on n, comma 1, and then it's the constant function 1. Okay, so that's a half. I mean, I won't bother writing down the formula because we can all do that. Okay, so that describes a sequence of functions in this set. Okay, so what I've got is an infinite number of metrics. So I can take each one of those metrics and I can ask the question, is this sequence Cauchy? Does it converge? That's a separate question for every p. And the answers could be different for every p. Okay? So what about p equals infinity? Okay, what do we know about this case? Well, I claim it neither converges nor is Cauchy. Well, I mean, that follows, right? I mean, if it was Cauchy, it would have to converge because with the d infinity metric, this is complete. And of course, if it converges, any convergent sequence is Cauchy. Right? But neither of those things is true. Why? Well, because the uniform limit of continuous functions is continuous. All the fn's are continuous, so if this converged, it would be to a continuous function, but then uniform convergence also implies pointwise convergence, and pointwise, these things converge. To the discontinuous function f of x, which is 0 for x less than a half when x is equal to a half, and 1 if x is greater than a half. Right? That's the... So the n is just shrinking this, right? So as I shrink it infinitely, it's just the thing that stays 0 all the way until a half. They all pass through this point. All the fn's have that point in common, so that's on the graph. And then, okay, so that's the function f. Certainly not continuous. Okay, so this can't converge, because if it did, it'd have to converge to that, and that's not continuous. All right. Okay, so the claim is that the sequence fn is Cauchy with respect to dp for all p not equal to infinity. Okay, similar sort of argument will show that, well, it can't actually converge, so that's a Cauchy sequence that doesn't converge, which shows these spaces are not complete. Okay, so. I mean, when I say convergence, it's always with respect to, well, in this case, not a metric. I mean, it's just pointwise, but here I'm saying converge. What do I mean? I mean with respect to the d infinity metric. Okay, so I claim it's Cauchy, but does not converge. All right, fine. But that means this f somehow will live in the completion, right? Just like when we took the completion of Q, we got R. That is, we took Cauchy sequences in Q. We got out the real numbers. If we take the completion of this function space with a dp metric, living in there are all Cauchy sequences, and that f is represented by a Cauchy sequence. Okay, so this f actually lives in the completion. It's a typical element of the completion. Okay, so proof of claim. All right, so I have to compute this, right? Convince you it's getting arbitrarily small. Well, I might as well compute its pth power. Right? I mean, I'm allowed to do that because taking a pth root is continuous. So if I can make this very small, I can make the pth root very small. Well, note that this quantity here, I guess I want to take one of them larger, right? Why is that? Well, just look at the picture. So I'm taking m larger, right? So this here is 1/2 minus 1 on m, and that's 1/2 plus 1 on m. Okay, so let me change my mind perhaps about what the green thing is. The green thing is now fm. So what's the absolute value of the difference between fm and fn? It's measuring these distances here. Okay, but the absolute value of the difference between fn and f is adding to this area the additional area which is up here and down there. Right? So it's bigger. Okay. Well, f might not be continuous, but it's still Riemann integrable, right? Because anything which is piecewise continuous is Riemann integrable, and piecewise means with respect to a partition, and here's a partition. 0 up to 1/2, and then 1/2, and then 1/2 up to 1. That's 3 sets, it's a partition, and this is continuous on it. Okay, so f is Riemann integrable, even though it's not continuous. So I'm allowed to write down expressions which integrate this kind of thing. Okay, so... Okay, so I've just got to evaluate this integral and then see that it gets arbitrarily small as n gets large. Okay, the details are in the notes, it's not very interesting. So you know what f is, right? There's a formula for it. And that integral is symmetric around 1/2, so I just get twice whatever I get by integrating from 1/2 to 1. And between 1/2 and 1, f is just 1. So that looks something like the integral from 1/2 to 1 of 1 minus fn. Fn is given by some, it's just a line, all right? So you're just integrating x. Okay, so you do the calculation and you get, I did the pth root, so whatever. It's then some number which doesn't depend on n. We don't care. Okay. All right. So as n gets infinitely large, that gets infinitely small. So that's it. All right. Okay, so that's a Cauchy sequence. All right, so let me give the argument that it can't converge. So that's based on the following observation. So take any subinterval of 0, 1, and then look at the function which takes a real valued function on 0, 1 and restricts it to that subinterval. Okay, that's a function. I claim it's continuous when I put the dp metrics on both sides for any p. Well, I mean, it's true for infinity. We knew that already. We've been using that over and over, that this kind of thing is continuous. Okay, so the new information is that it's true for p less than infinity, and that's an easy check using the properties of the Riemann integral. Okay, so that's continuous. So suppose, for a contradiction, that this sequence actually did converge to some continuous function with respect to dp. Right? I mean, to say it converges is to say it converges to a point in my space, and my space is made up of continuous functions. So when I say this, I mean G is continuous. Well, then, so that's convergence here with respect to dp. If I apply a continuous map to a convergent sequence, it remains convergent. So that means that the Fn is restricted to, well, let's say 0a, a anything less than a half, converges to G 0a with respect to dp. But that would tell you that G has to be identically 0, right? Because these are constant functions. Well, for sufficiently large n. Right? If I make n sufficiently large, then that little bit around a half shrinks so that it's past a. So these guys become just constant function 0. So this converges to the 0 sequence. And that tells me that G restricted to this has to be the 0 function, and similarly G restricted, so that means G of x is 0 for all x less than a half, and similarly GA1, a greater than a half is 0, therefore G of x is 1, for x greater than a half. Okay, but you can't have a continuous function doing that. All right, so G can't exist. All right, so at least for the interval 0, 1 and p less than infinity, you're convinced that this space is not complete. Okay, but you've also seen now an instance of a Riemann integrable function, namely f, which is not continuous, but nonetheless is the limit, well, is, you imagine the limit in some sense of a Cauchy sequence of things which are continuous, right? So by forming the completion of this space with respect to dp, one of the things you're adding into your space is exactly this Riemann integrable but not continuous f. All right. Okay, so if I take a normed space, and then I look at the associated metric, I can ask whether the resulting metric space is complete. If it is, I call the original normed space a Banach space. Okay, so Banach space just means complete normed space. So these are the sort of basic objects of infinite dimensional analysis. Well, you know a couple of Banach spaces already. Right? Because D infinity, that's complete, so that's a Banach space for free. We already proved that. Well, there's a special case. If you take X to be a finite set of points, then you'll see that Rn with the sup norm is Banach, and Cn with that. So that's the sum of the absolute values of the coefficients in a vector. That's also a Banach space. Well, but then I can take this infinity away and put a p, right? Because the p norm, the associated metric is dp, and that's Lipschitz equivalent to the d infinity metric. And so the resulting thing is complete because it's complete for infinity. So these are all, as metric spaces, basically essentially the same. Okay, so for free I get these are Banach spaces. Okay, so that's the finite dimensional case. Nothing really very interesting happening there, but anyway, they're Banach spaces. Okay, so the aim now is to start with this normed space, which is not a Banach space. It's not complete necessarily, unless X is finite. We're going to complete it by adding in formally all limits of Cauchy sequences, and that'll work. So that'll give us not just a metric space, but actually a normed space. The resulting normed space we call LP XF, and that's going to be a Banach space. All right. Okay, so there's two parts to that, one of which is extending functions from a dense subset, and another one which is just setting up the completion, and maybe I'll do the second part first. Yeah, something happens. Let's. How's that? Well, I could be less cheeky. I mean, it's something like a functor. So it's a construction which assigns to the kind of thing on the left-hand side, in this case a normed space, the kind of thing on the right-hand side, which is a Banach space. And moreover, linear transformations which have continuous linear transformations of normed spaces will give rise to continuous linear transformations of Banach spaces. So, okay, a technical word for work is functor. Okay, so I'm going to be brief with this lemma because we've seen something essentially equivalent in a tutorial already. So take a metric space. Then I can consider Cauchy sequences in a metric space. Say F and G. And I can define a relation between Cauchy sequences tilde means that the limit as n goes to infinity of the sequence of real numbers dfngn is 0. Then you can check that that's an equivalence relation on the set of Cauchy sequences. Okay, you check something very similar but a little different in topological groups, and it's not difficult, so I'm going to skip it. Okay, so what we're going to do is then take our metric space, take the set of all Cauchy sequences, impose this relation, that's some new set, then we're going to define a metric on that set, prove it's a metric space, prove it's complete, and then that's at least the first step of this. Then we have to prove that it isn't just a metric space, but a norm if we start normed space, if we start with a normed space. Okay. So. So x hat means the set I just described. So it's the set of Cauchy sequences modulo that relation. I mean, maybe it's worth being very explicit about the fact that this notation is slightly imprecise, right? Because I really might say d Cauchy. This relation here is not just associated to x. It certainly depends on d, right? Because that's what defines the equivalence relation. So if I have the same set with many different metrics, a given sequence might be Cauchy or not with respect to the different ones. Okay. So what I really mean is, given we're going to consider in a minute the same set but with many different metrics, it's important to keep in mind that the completion I get will be different even as a set for the different metrics. All right, so I'm about to claim that that can be turned into a metric space. So how do I define the metric? So I need to take So I want to define the distance between two Cauchy sequences, or more precisely, two equivalence classes of Cauchy sequences. So, maybe strictly speaking, I should put a little box there. It's even less readable. So we'll have to check it's well defined in a second, right? That's why I'm saying that. So what I'm about to write isn't a priori even sensible, because it needs to be independent of the choice of representative. Okay, well, what can I do? Well, I can just copy this, right? I can take the distance between fn and gn and take the limit as n goes to infinity. Okay, well, there's two things to check before that even makes sense. One is that this sequence actually converges to something, otherwise I'm not allowed to just say take the limit. And the second thing is that the number I get, presuming it actually is a number that's well defined, that it's independent of the choice of representative of the equivalence classes. Okay, so there's at least two things I need to check. And then I need to check that that actually satisfies the axioms for a metric. Okay. Now let's keep adding to our laundry list. So this metric space is complete. Not only is it complete, but it contains X as a dense subset. Okay, so when I write this, what I mean is a function from X to X hat. That's just going to sit an element of X as the constant sequence inside X hat. It's distance preserving, therefore it's automatically injective. And the image is dense. Okay? Hence the term completion. Right? We sat X inside a complete metric space in such a way that it's dense. Okay, so that's what we're going to do. Before I get into the details, is there any question about what we're trying to show? So I'm going to probably run out of time before I finish the story, so let me say it now. So the first step here was to take this, just forget the norm, but remember the metric, and then I complete the metric space. Okay, so this is completion. So that'll give me something. That's a complete metric space. And then I'm going to define a norm on this, which induces this metric, and that's going to be this thing. That'll be probably next lecture. There's a question, yeah. What does the word canonical mean? It means if you randomly sampled someone, they would always write down the same thing.
It means like the obvious choice.
Yeah, it's actually a bit of a subtle question, what canonical means. It's more of a meta-mathematical term. But in this case, it means, well, okay. If V is finite dimensional, V is always isomorphic to V dual. V is a vector space. But there's no canonical isomorphism. To write down an isomorphism, I have to choose a basis. Once I've chosen a basis, there's an isomorphism, because any two vector spaces of the same dimension are isomorphic, right? If V and W have dimension 5, well, pick a basis, match them up, that's an isomorphism. But that depended on choices. So it's not the case that if you randomly pick two people and said, write down an isomorphism, and don't use any other information or try not to, they'd automatically come up with the same thing. So there's not something implicit in the structure of the theory which tells you how to identify these two things. However, there is such an intrinsically defined, independent of all other choices, map like that. That's sort of what it means. But people argue about what is and what is not canonical. So, okay, so let's get into the proof. Okay, so I need to show this is well defined, first of all. That has two parts, as I said. One is actually checking that that sequence even converges. But that's okay, because the metric is continuous, right? So, and moreover, if I have two Cauchy sequences in X, then just pairing them up is a Cauchy sequence in X cross X, right, with the product metric, as you guys all know from the assignment. Okay, so it's a Cauchy sequence here, and well, if I have a Cauchy sequence in a metric space and a continuous map, then its image is Cauchy. All right, but R is complete, so it has a unique limit, so I'm entitled to write down that. Okay, so that shows that once I've chosen representatives from the equivalence classes, this number is well defined. But now I actually have to check that it's not dependent on the choice of representatives. Now in principle, that means I need to fix this guy, choose a different representative here, and fix that guy, choose a different representative there, and prove that it's independent of either maneuver. But this is symmetric, because the distance here is symmetric. So actually I only need to check it fixing a representative there and taking two different representatives in the first variable. Okay. Okay, so suppose I had another Cauchy sequence representing the first equivalence class. Well, we can just play the same game. Okay, so with respect to the induced metric on x cross x, these pairs satisfy the equivalence, as you'll see if you just write out what the distance is between them. And therefore, applying d, they must be equivalent as well. But if two Cauchy sequences are equivalent, that says precisely that their limits are going to be the same. So. I don't know if that's what I wrote down in the notes, or maybe I did it by hand. Okay, so that shows that this number is well defined. Okay. All right, so I've got to show it's a metric. Well, we already argued for the first part of the axiom that the distance is 0 if and only if the things are equal. So maybe symmetry is similarly obvious, so maybe I'll just do the triangle inequality. Okay, so I've got three Cauchy sequences in X. Well, for each fixed n, the triangle inequality works in X, right? So I've got the distance from Fn to Hn is less than or equal to the distance going via Gn. Which, if you like, says that this quantity is negative, non-positive, I suppose. Okay, so what's that? That's a sequence of real numbers less than or equal to 0. The set of real numbers less than or equal to 0 is closed. So if that sequence has a limit, then it must also be less than or equal to 0, because the limit would be an adherent point of this sequence. Well, we know that sequence has a limit because that's part of what we just showed. All the individual things have limits, and therefore taking the limit of the whole thing exists. That, well, limits commute with sums and multiplication by -1. So the limit of this is just precisely d hat of the f's. I hope it's clear what this means. This means fn, n equals 0 to infinity. So that's fg. And that's gh. And just rearranging that, taking those two terms over the other side, we get the desired inequality for d hat. Okay, so that's the triangle inequality, and the other ones were straightforward, as I said, so we've got ourselves a metric space. I have precisely 2 minutes to do the rest. Okay, so let's just do that X is dense. Okay, so the map from X to X hat is just constant sequences. Those are Cauchy, obviously. Right, so that's well defined, and it's distance preserving, right? Because d hat of a constant sequence X to a constant sequence Y is the limit of a constant sequence dxy. All right, so it's clearly distance preserving and therefore injective, and I just need to show that it's dense. So how do I do that? Well, I just take an arbitrary element of x hat, and I need to provide a Cauchy sequence, which is, so there's x hat, there's x. I've defined an injective map. I'm just going to identify x with its image, and I need to prove that any element in the target metric space has some Cauchy sequence in that subset converging to it, or has a convergent sequence in the subset. Well, if you just unpack what f is, it tells you what that sequence is, right? Because anything in x hat looks like xn, n to infinity. I mean, the points of x hat are Cauchy sequences. All right, so what am I claiming? I'm claiming that the sequence, which is the constant sequence x0, okay, that's a point in x hat, right? That doesn't change, it's a constant sequence. And then I take x1, the constant sequence. That's a Cauchy sequence, it's another point in x hat. Okay, so that gives me a sequence of Cauchy sequences, if you get my meaning. All right, that's a sequence in x hat, but not just in x hat, it's in the image of x, because they're all constant sequences. So I just need to convince you that that sequence in x hat converges to f with respect to d hat. Right? Okay. So what is the nth term of this sequence of Cauchy sequences? It's the sequence, the constant sequence xn. All right, so let me take d hat f, comma, the nth term of that sequence, which is the constant sequence all right, well, the limit here I take is not the n's, right? It's the limit over the things that live in the sequence, which I'm now indexing by m. So that's the limit as m goes to infinity, d of x m, that's the mth term in f, comma, the mth term in this guy, and that's just x to the n because it's always, sorry, xn, because that's always xn. All right, so that's the d hat distance from f to this. Okay, so to show this sequence, as I vary n, converges to f, I just have to show that this can be made arbitrarily small by making n arbitrarily large. But that's the definition of Cauchy, right? Right? To say the sequence x is Cauchy is to say, given any epsilon, as long as I make both m and n very large, I can make this distance less than epsilon. But I'm allowed to make both m and n very large, because this guy is going to infinity, and I'm allowed to make this as large as I like. Okay, so we just spell that out. The fact that this is a Cauchy sequence says precisely that I can arrange for that converges to 0 as m goes to n. Sorry. That number, which only depends on n, because I'm taking this limit, this number as a function of n goes to 0 as n goes to infinity. Okay, so that proves that x is dense. And then I've got to still prove that x hat is complete, but I've run out of time, so I'll have to do that next time.